A strange sun hangs in an orange sky above an alien shore. You are standing on a world that is not Earth, looking up at a light that is not our own. This is not just science fiction. It is the ultimate destination of a search happening right now, a hunt for planets in what astronomers call the Goldilocks Zone. This is the narrow band of space around a star where conditions are just right, not too hot and not too cold for a planet to potentially host liquid water and maybe even life. We are scouring our galaxy for Earth 2.0. By the end of this, you will understand not only how we find these worlds, but what it would truly mean to live on one. We will explore why a planet like Venus inside this perfect zone became a hellscape, and how a frozen desert like Mars may once have been a cradle for life. The cosmos is whispering its secrets, and we are finally learning how to listen. What does it mean for our future if the universe is full of just right worlds? That alien shoreline you stand upon exists within a very specific slice of cosmic geography. Finding it requires understanding the habitable zone, the single most important concept in the search for life beyond Earth. But this is not a simple, fixed address. Think of it not as a line on a map, but as a moving target, a shifting ring of possibility that depends entirely on the star at the center. It is the range of distances from a star where a planet with a suitable atmosphere could maintain liquid water on its surface. The key word there is could, because the habitable zone does not guarantee a habitable planet. It simply marks the place where the conditions are plausible, a starting point in the vast cosmic real estate market. Why does this zone shift? It all comes down to the star's personality. A massive, blazing blue giant star pours out such ferocious energy that its habitable zone is pushed incredibly far out, a distant and lonely orbit. Meanwhile, a small, cool red dwarf star glows with a faint, ruddy light. Its habitable zone is so close that a planet there would be tidally locked, one side in permanent day, the other in endless night. For a star like our Sun, a stable yellow dwarf, the zone is a comfortable middle ground. To visualize this, picture a campfire on a cold night. Stand too close and you get scorched. Stand too far away and you feel no warmth at all. There is a sweet spot in between where the heat is just right. A planet is like a person at that cosmic campfire, its distance determining its fate. Astronomers measure this using two key ideas. The first is stellar flux, which is simply the amount of the star's energy that hits each square meter of the planet. Too much flux and oceans boil away, too little and they freeze solid. The second is equilibrium temperature, a basic calculation of how hot the planet's surface would be if it had no atmosphere at all, just absorbing and radiating the star's heat like a bare rock. This is where the magic of an atmosphere comes in. An atmosphere acts like a blanket, trapping heat and redistributing it around the planet. Venus, which sits inside our Sun's habitable zone, has an equilibrium temperature that should be quite pleasant. But its thick, choking carbon dioxide blanket created a runaway greenhouse effect, turning it into a scorching hellscape. Mars, on the outer edge, has a thin blanket that cannot hold enough heat, leaving it frozen. This complexity is why scientists often talk about two different zones. The conservative habitable zone is the stricter model. It assumes a planet has an Earth-like atmosphere of nitrogen and carbon dioxide, a cautious estimate for where life as we know it could persist. The optimistic habitable zone casts a wider net. It considers planets with thicker atmospheres that could trap more heat, or those with alternative greenhouse gases, allowing worlds farther from their star to potentially host liquid water. It is the difference between searching for a perfect Earth twin and wondering about the strange, unexpected cousins we might find. So the next time you hear about a planet in the habitable zone, remember it is not a promise of a blue marble, but an invitation to a deeper mystery. What kind of world is it really, and what story does its atmosphere tell? The fate of a Goldilocks world is written in the light of its star. Not all suns are created equal, and the type of star at the center of a system dictates everything about the possibility of life within its habitable zone. Our own star, the Sun, is a G-type yellow dwarf. It is stable, middle-aged, and remarkably consistent in its output, offering a steady stream of energy for billions of years. This longevity is the most crucial gift a star can give. Life on Earth took hundreds of millions of years to go from simple single-celled organisms to complex animals. A stable, long-lived star provides the time for that improbable chemical experiment to unfold. But our Sun is just one personality type in a galactic neighborhood full of extremes. On one end of the spectrum are the Titans, the O and B-type stars. These are the brilliant blue giants, many times more massive and hotter than our Sun. They flood their systems with intense ultraviolet radiation and stellar winds. While they do have a habitable zone, it is pushed far out into space by their sheer fury. Their fatal flaw is their lifespan. They burn through their nuclear fuel at a breakneck pace, living for only a few million years before exploding in spectacular supernova. That is a cosmic blink of an eye, likely not enough time for life to even begin, let alone evolve into something complex. A planet in their habitable zone would see its sun die before it could ever tell its story. On the opposite end are the most common stars in the galaxy, the M-dwarf red dwarfs. Stars like Proxima Centauri, the closest star to our own sun, are small, cool, and incredibly frugal with their fuel, allowing them to shine for trillions of years. Their habitable zones are therefore very close in, which creates a unique and challenging environment. A planet orbiting that close is almost certainly tidally locked, meaning one hemisphere permanently faces the star in eternal daylight, while the other is turned away in perpetual frozen night. For a long time, scientists thought this would make such worlds uninhabitable, with one side scorched and the other an icy wasteland. But new climate models suggest a strange possibility. If such a planet has a thick enough atmosphere to circulate heat, the region between eternal day and endless night, the terminator line, could maintain a temperate climate. This could create what astronomers call an eyeball Earth, a world where a liquid ocean exists in a circular band around the star-facing side, resembling the iris of an eye surrounded by global ice. It is a bizarre and beautiful concept, a sliver of habitability clinging to the twilight zone of a dim red sun. So the search for life is not just about finding a planet in the right place, but about finding one orbiting the right kind of star with the right temperament and enough patience to allow for miracles. But distance from the star is only the first line on a much longer checklist. A planet can sit perfectly in that sweet spot and still be a barren, airless rock or a crushing, toxic gas giant. True habitability requires a delicate convergence of many other factors, a symphony of conditions that must all play in harmony. The first is planetary mass. A world needs to be heavy enough with sufficient gravity to hold onto a life-sustaining atmosphere. Think of a planet's gravity as the hand that clasps its atmospheric blanket. If the hand is too weak, the blanket slips away, stripped by solar winds over eons. Mars is a tragic example of this, a world that likely once had flowing water but was too small to keep its protective gases from leaking into space. On the other hand, a planet that is too massive, like a mini Neptune, will hold onto an atmosphere, but it will be a deep, crushing envelope of hydrogen and helium, with no solid surface to stand on at all. So the Goldilocks principle applies to size as well, not too small, not too big, but just right to cradle a breathable sky. Next, we must consider what the planet is made of, its composition. We are looking for terrestrial or rocky worlds like Earth, Venus, and Mars with a solid surface of silicates and metals. A gas giant, no matter where it orbits, offers no ground for oceans to pool or life to take root. But being rocky is not enough. The planet must also have the right ingredients, the essential elements for life as we understand it. Carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur, often abbreviated by scientists as CHNOPS, are the fundamental building blocks of organic chemistry. They must be present and accessible, likely delivered long ago by asteroids and comets in the system's chaotic youth. Then there is the hidden engine of a living world, geological activity. A planet with a molten, churning interior is a planet that recycles. This tectonic activity is crucial for the carbon silicate cycle, a planetary thermostat that regulates climate over millions of years. Here is how it works in simple terms. Volcanoes release carbon dioxide into the atmosphere, which traps heat and warms the planet. That warmth allows rain to fall, and the rainwater, slightly acidic, weathers rocks on the surface. This weathering pulls carbon dioxide out of the air, locking it into minerals that are eventually carried down into the planet's mantle by tectonic plate movement. Later, volcanoes release it again. This beautiful, slow-motion loop prevents a planet from veering into either a permanent icehouse or a runaway greenhouse. Furthermore, that molten core, spinning like a dynamo, generates a global magnetic field. This magnetic field is a planet's shield, deflecting the deadly charged particles of the stellar wind that would otherwise erode the atmosphere and bathe the surface in harmful radiation. Without this invisible force field, even a thick atmosphere is vulnerable. Finally, we come to the most iconic requirement, liquid water itself. Water is the universal solvent, the medium in which the molecules of life can meet, mix, and react. It is not enough for water to simply exist as ice in the crust or vapor in the air. It must be stable as a liquid on the surface for extended periods. This depends on that perfect cocktail of atmospheric pressure and temperature we discussed earlier. So when we discover a new world in the habitable zone, the real investigation is just beginning. We must ask, does it have the mass to hold an atmosphere, the geology to regulate its climate, the magnetism to protect its skies, and the chemistry to brew the soup of life? Being in the zone opens the door, but it takes all these other factors to make a house a home. Earth stands alone in the cosmos. The only world we know for certain is alive. It is our blueprint, the master template against which we measure every other candidate in the habitable zone. So what makes this pale blue dot floating in the vast emptiness so perfectly suited for life? It begins with its prime real estate, orbiting our Sun at an average distance of about 150 million kilometers. This places us squarely in the middle of the Sun's conservative habitable zone, receiving just the right amount of solar flux to keep water liquid. But location was just the starting gift. The true story of Earth's habitability is one of dynamic balance, maintained by a series of interconnected systems working in concert over 4.5 billion years. Our atmosphere is the first layer of that balance. It is not too thick like Venus's crushing shroud, and not too thin like the wispy veil of Mars. It is a blend of nitrogen and oxygen, with trace amounts of greenhouse gases like carbon dioxide and water vapor that act as a precisely tuned thermostat, trapping just enough heat to keep our global average temperature around 15 degrees Celsius. This breathable sky is held in place by our planet's mass, which provides enough gravity to prevent gases from escaping into space too quickly, but an atmosphere alone is vulnerable. That is where Earth's churning, metallic core comes in. Its rotation generates a powerful magnetic field, a vast, invisible shield that deflects the Sun's constant stream of charged particles. Without this magnetosphere, our atmosphere would have been slowly eroded by the solar wind, likely leaving us as barren and exposed as Mars. Then there is the planet's living geology. Earth's crust is broken into tectonic plates that slide, collide, and dive beneath one another. This relentless motion drives the carbon silicate cycle, the planetary climate regulator we touched on earlier. When carbon dioxide levels rise and the planet warms, increased rainfall and rock weathering pull more carbon out of the atmosphere, cooling things down. When it gets too cold, volcanic activity, driven by that same tectonic movement, releases stored carbon dioxide back into the air, warming the planet again. It is a slow, beautiful feedback loop that has maintained a relatively stable climate for eons despite a major cosmic puzzle. Scientists call this the faint young sun paradox. Models show that our sun was about 30% dimmer in its youth. By all rights, early Earth should have been a frozen snowball, yet geological evidence shows it had liquid oceans. The solution likely lies in that same carbon cycle. A much thicker early atmosphere, rich in potent greenhouse gases like methane and carbon dioxide, provided an extra blanket of warmth, compensating for the fainter sunlight. As the sun grew brighter over billions of years, life itself began to participate in the regulation. The rise of photosynthetic organisms like cyanobacteria started pulling carbon dioxide out of the air and releasing oxygen, gradually transforming the atmosphere into the one we breathe today. This introduces the most profound element of Earth's blueprint, the co-evolution of the planet and the life upon it. Our vast oceans, covering 70% of the surface, are not just a reservoir of water. They are the cradle where life began, a global circulatory system that distributes heat and nutrients, and a key component of the climate system. Earth did not simply find a habitable zone and stay there. It actively built and maintained its own habitability through geology, chemistry, and eventually biology in a continuous dance with its star. This sets the ultimate benchmark. When we look at a distant exoplanet in a habitable zone, we are not just asking if it is in the right place. We are wondering, does it have the systems, the dynamism, the resilience of Earth? Does it possess that miraculous ability to keep itself alive? Yet for all its perfect balance, Earth's story could have easily gone another way. Just next door, a world spins in a silent, searing warning. Venus, named for the goddess of love, is a vision of cosmic irony. It orbits well within the Sun's habitable zone, closer to the inner edge, and is often called Earth's twin due to its similar size and composition. But the resemblance ends there. Venus is a crushing, scorching hellscape with surface temperatures hot enough to melt lead and an atmospheric pressure 92 times greater than Earth's at sea level. It is the ultimate cautionary tale of how a planet in the perfect spot can go catastrophically wrong. So what happened? The story of Venus is a story of a runaway greenhouse effect, a process that began with water. Scientists believe early Venus likely had vast oceans, just like Earth, but being closer to the Sun, it received more solar energy. This caused its oceans to begin evaporating at a higher rate, pumping enormous amounts of water vapor, a potent greenhouse gas, into the atmosphere. This trapped more heat, which evaporated more water in a vicious, self-reinforcing cycle. As temperatures soared, the water vapor high in the atmosphere was broken apart by solar ultraviolet radiation. The lightweight hydrogen atoms escaped into space forever, while the oxygen was left behind to combine with other elements. This was the point of no return. Venus lost its water permanently. With the oceans gone, there was no liquid left to absorb carbon dioxide from the atmosphere through processes like rock weathering. Meanwhile, volcanic activity continued to pump more and more carbon dioxide into the air. On Earth, our oceans and rock cycles steadily draw carbon dioxide down and lock it away. On Venus, with that thermostat broken, the carbon dioxide simply built up and built up, creating the incredibly thick, toxic atmosphere we see today, composed of over 96% carbon dioxide. This dense blanket traps heat with staggering efficiency, creating the extreme surface conditions. But the tragedy of Venus may have been compounded by another missing piece, a planetary shield. Unlike Earth, Venus lacks a global magnetic field generated by a churning metallic core. While its core may have once been active, it is thought to have cooled and solidified, or perhaps it simply does not spin in the right way to generate that protective dynamo. Without this magnetic shield, the solar wind, a stream of charged particles from the Sun, struck Venus's upper atmosphere directly over eons. This likely helped strip away not only the hydrogen from those broken water molecules, but also any other lighter atmospheric gases, leaving behind the heavy, suffocating blanket of carbon dioxide. Venus teaches us a brutal lesson about the inner edge of the habitable zone. It is not a sharp boundary, but a zone of danger where the delicate balance of a climate system can be tipped into a fatal feedback loop. A planet here walks a tightrope. It must have just the right atmospheric composition and geological activity to regulate its temperature, or the heat from its star will trigger an irreversible catastrophe. Venus shows us that being in the Goldilocks zone is not a guarantee of comfort. It is merely an opportunity, one that requires a planet to possess its own set of internal brakes and balances to avoid spiraling out of control. Our neighbor is a stark monument to a path Earth itself narrowly avoided, a ghost of a world that drowned in its own sky. If Venus is a warning about the inner edge, Mars represents the quiet tragedy of the outer frontier. This cold, red desert hanging on the far side of the Sun's habitable zone tells a story of loss. Today, its surface is a frozen, radiation-scoured wasteland, with an atmosphere so thin it is less than 1% of Earth. Yet, etched into its barren skin is undeniable evidence of a different past. Orbiting spacecraft have captured stunning images of what look like dry riverbeds, vast networks of valleys that branch and weave across the landscape, just like water-carved channels on Earth. We see the ghostly outlines of ancient lake beds and deltas where rivers once emptied. Minerals that only form in the presence of persistent liquid water cling to the rocks. The conclusion is inescapable. Billions of years ago, Mars was a wet world. It likely had rivers, lakes, and perhaps even a shallow ocean in its northern lowlands. For a window of time, it was a planet firmly within the conditions for life, a second blue marble in our solar system. So what happened? How did a world with flowing water become a freeze-dried relic? The answer lies in a combination of its place in space and its fundamental physical shortcomings. The first blow was its location. Being on the outer fringe of the habitable zone meant Mars always received less solar energy than Earth. Its equilibrium temperature was inherently colder. To compensate and maintain liquid water, it would have needed a much thicker atmosphere with strong greenhouse gases like carbon dioxide or methane to trap every bit of that faint sunlight. Evidence suggests it once had such an atmosphere, but it could not hold onto it. This is where the second and perhaps most critical factor comes in: planetary size. Mars is only about half the diameter of Earth and just over 1/10 its mass. This smaller size had two devastating consequences. First, its interior cooled much faster. A planet's internal heat is a remnant of its violent formation, and smaller objects lose heat more quickly than larger ones. As Mars's core cooled, the churning of molten metal that generates a global magnetic field slowed and then stopped. Without this protective magnetic shield, the solar wind, that relentless stream of charged particles from the Sun, had direct access to the Martian atmosphere. Over hundreds of millions of years, this wind stripped the atmosphere away molecule by molecule, a process called atmospheric sputtering. The planet's relatively weak gravity, another result of its small mass, could not hold on as the gases were torn into space. As the atmosphere thinned, its ability to trap heat vanished, temperatures plummeted, any remaining surface water froze solid, with much of it locking away in polar ice caps or deep underground as permafrost. The atmospheric pressure dropped so low that liquid water became impossible, instantly boiling away in the near vacuum even if it did melt. The planet's geological engine, likely never as vigorous as Earth's, ground to a halt. Without tectonic activity to recycle carbon and regulate climate, Mars had no way to recover. It transitioned from a potentially habitable world to a static, frozen desert, its watery history preserved only in sterile geology. Mars teaches us a somber lesson about the outer edge of the habitable zone. It is a place of fragility where a planet's own physical stature determines its fate. A world here needs every advantage: a robust size to maintain a hot core and a strong magnetic shield, a thick initial atmosphere, and active geology to keep its systems running. Without that inherent resilience, the slow leak of heat and atmosphere into the cold cosmos is inevitable. The red planet is not just a neighbor, it is a fossil, a monument to a habitable era that slipped away, showing us that a place in the zone is a temporary lease, not a permanent deed. Finding these Goldilocks worlds around other stars is a feat of cosmic detective work. We cannot see them directly with telescopes, tiny specks lost in the blinding glare of their suns. Instead, we must observe the subtle clues they leave behind, the faint fingerprints on the light of their star. Two primary methods have revolutionized this search, turning speculation into a catalogue of thousands. The first is the transit method. Imagine you are watching a streetlight from a distance and a moth flies directly across your line of sight. For a moment, the light dims ever so slightly. Astronomers do this on a stellar scale. They use sensitive instruments like those on the Kepler and TESS space telescopes to monitor the brightness of hundreds of thousands of stars, looking for those periodic, telltale dips in light. When a planet passes or transits in front of its star from our viewpoint, it blocks a tiny fraction of the starlight. This simple observation reveals a wealth of information. The depth of the dip tells us the planet's size relative to its star. A bigger planet blocks more light. The timing of the dips reveals the planet's orbital period, how long its year is. From that, using the laws of orbital mechanics, we can calculate its distance from the star. And knowing both its distance and the star's temperature lets us estimate the planet's equilibrium temperature, whether it is in that coveted habitable zone. The second cornerstone technique is the radial velocity method, often called the wobble method. A planet does not orbit a stationary star. Instead, both the star and the planet orbit their common center of mass. Because the star is so much more massive, this center of mass lies very close to, or even inside, the star itself. The result is that the star makes a tiny, rhythmic wobble as the planet tugs on it. We detect this wobble through the Doppler effect in the star's light. As the star wobbles toward us, its light is compressed, shifting slightly toward the blue end of the spectrum. As it wobbles away, the light stretches, shifting toward red. By meticulously measuring these shifts in the star's spectral lines, astronomers can detect the gravitational tug of an unseen planet. The size of the wobble reveals the planet's minimum mass. The rhythm of the wobble again gives us the orbital period. When used together, transit and radial velocity data are incredibly powerful. Transit gives us the planet's size, radial velocity gives us its mass. Combine them, and we get the planet's density. Is it a dense, rocky world like Earth, or a puffy, gaseous world like Neptune? This is how we begin to classify these distant worlds. Beyond these workhorses, other methods glimpse more challenging targets. Direct imaging is exactly what it sounds like, using advanced coronagraphs to block the star's blinding light and trying to capture the faint glow of the planet itself. This is exceptionally difficult, like trying to photograph a firefly next to a searchlight from miles away, but it has succeeded for a few young, hot, giant planets far from their stars. Gravitational microlensing is a more indirect and rare method. It relies on the gravity of a foreground star acting as a lens, magnifying the light of a background star. If a planet orbits the foreground star, it can create a distinctive blip in the magnified light curve. This method can detect planets at great distances, even floating freely between stars. Each technique is a different tool, allowing us to piece together the portrait of a world we will never visit, measuring its dance around its sun from across the staggering void. The silent census of the cosmos began with a single, unblinking eye in the dark. In 2009, NASA Kepler Space Telescope launched on a singular mission to stare at a fixed patch of sky near the constellations Cygnus and Lyra. Its goal was not to take pretty pictures, but to perform a relentless, years-long photometric survey, measuring the brightness of over 150,000 stars with exquisite precision, hunting for those telltale dips caused by transiting planets. What it found did not just add to our knowledge, it shattered our cosmic perspective. Kepler revealed a galaxy that is not lonely but teeming with worlds. The statistics it gathered are staggering. Based on Kepler's data, astronomers now estimate there are more planets in our Milky Way galaxy than there are stars. Think about that for a moment. Our galaxy contains somewhere between 100 and 400 billion stars, and there are more planets than that. This simple, profound fact means planets are not rare accidents, but a fundamental, common outcome of star formation. The universe is building them by the billions. When you look up at the night sky, every point of light you see is not just a sun, but likely the center of its own system of worlds. Navigating this flood of discovery requires understanding two key terms. A planet candidate is a potential world identified by Kepler's data, a promising dip in starlight that has all the hallmarks of a transit but awaits confirmation by other methods. A confirmed exoplanet is one that has been validated, often through follow-up observations with ground-based telescopes using the radial velocity method, proving it is real. Kepler's legacy lies in those numbers, in the thousands of candidates and confirmed planets it gifted to science. But among those thousands, a few specific discoveries changed everything. Planets like Kepler 452b, often called Earth's older cousin, it orbits a sun-like star in the habitable zone, is about 60% larger than Earth, and has a 385-day year. It was a signal that worlds of a familiar scale existed in the right place. Then there were the planets of the Kepler 186 system, or the remarkable, compact system of 7 Earth-sized worlds orbiting the red dwarf star TRAPPIST-1, 3 of which sit squarely in the star's habitable zone. These were not gas giants, they were small, rocky targets, the very type we needed to find. Kepler's greatest revelation was this demographic shift. Before Kepler, the first exoplanets we found were often hot Jupiters, massive giants orbiting perilously close to their stars simply because they were the easiest to detect. Kepler showed us that small planets, from Earth-sized to super-Earths, are actually the most common type in the galaxy. The telescope's primary mission ended when its reaction wheels failed, but its data pipeline continues to yield new discoveries years later. It taught us that the habitable zone is not a barren theoretical line, but a neighborhood that is likely crowded with real estate. We went from wondering if other Earths existed to knowing, statistically, that they must. The question was no longer if, but which one we would look at next. Kepler taught us the galaxy was full of worlds, but it left us with a new challenge. Most of the stars it monitored were faint and distant, hundreds or thousands of light years away, making detailed follow-up observations incredibly difficult. We needed a new hunter, one that could find planets right in our own stellar backyard. That hunter is the Transiting Exoplanet Survey satellite known as TESS. Launched in 2018, TESS represents a fundamental shift in strategy. While Kepler stared deeply at one patch of sky, TESS is conducting an all-sky survey. It divides the entire celestial sphere into 26 overlapping sectors, observing each one for about 27 days before pivoting to the next. This methodical scan allows it to eventually cover 85% of the sky, an unprecedented cosmic census. But the genius of TESS is not just in its breadth but in its focus. It deliberately targets bright, nearby stars, primarily those that are 30 to 100 times brighter than the stars Kepler studied. Why does brightness matter so much? Because a planet orbiting a bright, close star gives us our best chance to look beyond its orbit and into its very atmosphere. Once TESS identifies a transiting world, the real work begins for the next generation of telescopes like the James Webb Space Telescope. These observatories rely on that bright, clean starlight to perform a technique called transmission spectroscopy. When the planet transits its star, a tiny fraction of the star's light filters through the planet's thin atmospheric rim. Different gases in that atmosphere absorb specific wavelengths of that light. By analyzing the intricate fingerprint of missing colors in the starlight, scientists can deduce the chemical composition of an alien sky, potentially detecting water vapor, methane, carbon dioxide, or even signs of pollution from an industrial civilization. TESS is finding the prime targets for this breathtaking next step. Its discoveries are already bringing the search for life closer to home. One of its most exciting finds is the TOI 700 system, a small, cool M-dwarf star just over 100 light-years away. TESS data revealed not just one, but several small, rocky planets orbiting this quiet sun. The outermost world, TOI 700e, is especially compelling. It is roughly 95% the size of Earth and orbits squarely within the star's conservative habitable zone. This means it receives about 86% of the stellar energy that Earth gets from the Sun, and if it has a suitable atmosphere, its surface could maintain liquid water. It is a world of profound possibility, a neighbor in cosmic terms, and a perfect candidate for the James Webb Space Telescope to study in exquisite detail. TESS is more than a successor, it is a bridge. It takes the statistical revelation of Kepler that small planets are everywhere and provides us with a curated list of the most promising, most accessible worlds to investigate. It is turning the abstract concept of the habitable zone into a catalogue of real addresses, places where we can finally begin to ask the most profound question of all. What fills the air on these distant shores? One world stands closer than any other, a whisper away in cosmic terms. In the quiet glow of Proxima Centauri, the star nearest to our Sun, astronomers discovered a rocky world, Proxima Centauri b. It is a landmark find, a roughly Earth-mass planet orbiting squarely within its star's conservative habitable zone, a mere 4.2 light-years from Earth. This makes it not just a candidate for life, but our closest exoplanetary neighbor, a frontier world hanging in the deep sky of our closest stellar companion. Yet, its address comes with extraordinary challenges because Proxima Centauri is not a calm, yellow sun like our own. It is a turbulent red dwarf, and its personality dictates everything about the possibility of life on this nearby world. Red dwarfs are famously volatile. They can erupt in powerful stellar flares, sudden bursts of radiation that can be hundreds of times more powerful than anything our Sun produces. A planet orbiting as close as Proxima b does, completing its year in just 11 Earth days, would be bathed in these intense pulses of X-rays and ultraviolet light. Such radiation could strip away a planet's atmosphere over time and bombard its surface with levels that would be lethal to most life as we know it. Furthermore, that tight orbit almost certainly means the planet is tidally locked. One hemisphere forever faces its dim red sun in perpetual, scorching daylight, while the other is turned away in eternal, frozen night. This creates a staggering temperature extreme, a world divided. The very light from a red dwarf is also different, peaking in the infrared part of the spectrum rather than the visible light that fuels life on Earth. For a long time, this combination of flares, tidal locking, and alien sunlight painted a bleak picture for Proxima b and worlds like it. They seemed to be in the right place for all the wrong reasons, tantalizingly close yet profoundly hostile. But science thrives on complexity, and new ideas are challenging that grim assessment. Could Proxima b be habitable despite these harsh conditions? The debate hinges on two critical buffers, atmosphere and ocean. A thick, planet-wide atmosphere could be a powerful shield and a global equalizer. It could absorb and scatter the harmful radiation from stellar flares, protecting the surface below. More importantly, a dense atmosphere can circulate heat from the permanent day side to the permanent night side, potentially smoothing out those brutal temperature extremes and creating a vast, temperate twilight band where conditions might be just right. Some climate models even suggest that with a sufficiently thick carbon dioxide atmosphere, the entire planet could maintain liquid water. The other possibility is a global, planet-encircling ocean. If Proxima b is a water world, its vast sea could act as a massive heat sink and transporter. Ocean currents, driven by the temperature difference between the hot and cold hemispheres, could circulate warmth around the globe, again creating milder conditions in the regions between light and dark. This could sustain an aquatic biosphere even if the land surfaces were uninhabitable. The presence of a strong magnetic field generated by a still molten core would further bolster its chances by deflecting the stellar wind and helping to preserve that crucial atmosphere. So Proxima Centauri b stands as the ultimate cosmic paradox, a world of profound possibility and profound peril, sitting right on our galactic doorstep. It forces us to expand our definition of a living world. Habitability may not require a perfect, sun-drenched globe like Earth. It might instead persist in the dynamic tension of a twilight ring, under the flickering light of a tempestuous red sun, protected by a sky we can only begin to imagine. The search for life demands not just a single candidate, but a laboratory. We find that laboratory 40 light-years away, orbiting a star so faint it barely outshines the planet Jupiter. This is the TRAPPIST-1 system, a cosmic revelation that redefined what a solar system could be. Around this dim, ultra-cool red dwarf star, astronomers discovered not one, not two, but 7 rocky worlds, all roughly the size of Earth or slightly smaller. They form a stunningly compact family, a planetary system squeezed into a space smaller than Mercury's orbit around our Sun. Here, years are measured in days. The innermost planet completes an orbit in just 1.5 Earth days, while the outermost takes about 20. This proximity creates a sky unlike any other. If you stood on the surface of one of these worlds, the neighboring planets would appear as distinct, magnificent orbs. Some larger than our moon appears from Earth, their cloud tops and geological features potentially visible to the naked eye. Several of these siblings, particularly planets E, F, and G, orbit within the star's habitable zone where liquid water could exist. But in such a tight-knit system, habitability is driven by forces far stranger than simple sunlight. The immense gravitational pull from the star and the intricate dance of the planets themselves create powerful tidal forces, stretching and squeezing their interiors. This constant flexing generates internal heat through a process called tidal heating. It is the same phenomenon that drives the volcanic fury of Jupiter's moon Io. On a TRAPPIST world, this internal furnace could maintain subsurface oceans of liquid water beneath a thick crust of ice, even on a planet that receives too little starlight to warm its surface. It is a hidden, geological warmth that could sustain life completely cut off from the dim red sun above. The compact orbits raise another breathtaking possibility: atmospheric exchange. The planets are so close that during periods of intense stellar activity, the outer layers of their atmospheres could brush against one another. It is conceivable, though speculative, that material, even primitive microbial life, could be transferred between these worlds on rocks blasted into space by asteroid impacts, a form of interplanetary cross-pollination. This makes TRAPPIST-1 the ultimate gift to comparative planetology. For the first time, we have not just one Earth-sized target in a habitable zone, but a complete set of siblings, all formed from the same stellar nursery, all orbiting the same star. With a James Webb Space Telescope, we can point its instruments at this one quiet star and study the atmospheres of multiple worlds in a single system. We can ask, why does one planet have a thick, Venus-like haze while another shows signs of water vapor? Why does one hold onto its atmosphere while another appears bare? By comparing these 7 worlds side by side, we will learn the rules of how rocky planets form, evolve, and perhaps become living worlds. This tiny, dim star holds a miniature solar system that may teach us more about the potential for life than any other discovery. A family portrait where every face tells a different part of the same cosmic story. A star catalogued as Kepler 452 shines in the constellation Cygnus, 1,400 light-years from Earth. Around this star, a planet completes its orbit once every 385 days, a rhythm strikingly familiar to our own 365-day year. This is Kepler 452b, a world that earned the title of Earth's bigger, older cousin. The similarities are haunting. Its parent star is a G-type yellow dwarf, nearly identical to our Sun in temperature and size, though slightly brighter. The planet itself orbits within that star's conservative habitable zone, receiving just about 10% more stellar flux than Earth does. If you could stand on its surface, the sunlight would feel almost indistinguishable from a sunny afternoon here at home. But the differences are where the true wonder lies. Kepler 452b is a super-Earth with a radius about 60% larger than our planets. This places it in a fascinating and mysterious category. With that increased size comes increased mass, likely several times that of Earth. What does that mean for its environment? The gravity would be stronger, perhaps 1.5 to 2 times what we experience. A 100-pound person here would feel like they weighed 150 to 200 pounds there. The atmosphere could be substantially thicker, potentially leading to immense surface pressure and a powerful greenhouse effect. It might be a world of vast, shallow seas covering continents smoothed by crushing weight, or perhaps a global water world with no land at all. Its geology would be profoundly shaped by its greater internal heat, possibly leading to more intense volcanic activity and a more dynamic, restless crust. Yet the most compelling detail is not about the planet but about its sun. The star Kepler 452 is about 1.5 billion years older than our Sun. This single fact ignites the imagination with a staggering implication. If Earth, around its 4.5 billion-year-old Sun, took roughly 1 billion years for simple life to emerge and another 3.5 billion to reach our technological civilization, then a planet orbiting a star 6 billion years old has had an extra 1.5 billion years of cosmic evolution. Consider what 1.5 billion years represents. On Earth, that span of time takes us from the first simple multicellular organisms in the oceans all the way to the present day, encompassing the entire saga of complex life. If life found a foothold on Kepler 452b, it has had an additional epoch to develop, adapt, and advance. What might exist there now? A biosphere of such complexity and sophistication that it defies our imagination. Perhaps photosynthesis there has evolved to use a different part of the stellar spectrum, painting the landscape in colors we cannot see. Perhaps intelligence, if it arose, has had millennia upon millennia to mature, solve its planetary challenges, and look outward to the stars. This world is a message in a bottle from the deeper past of the universe, showing us a potential future for our own planet and posing a question that hums across the void. In a cosmos that is overwhelmingly ancient, are we the newcomers just beginning our story while others have already written volumes? The ancient light from Kepler 452b carries a profound question, but some of the most promising answers may come from worlds that look nothing like Earth at all. A planet designated K218b orbits a cool red dwarf star 110 light-years away. For years, it was classified as a mini-Neptune, a world significantly larger than Earth but smaller than the ice giants in our own solar system. Astronomers assumed it was a gaseous planet, shrouded in a thick, hydrogen-rich atmosphere with no solid surface, a place utterly inhospitable to life as we know it. Then the data from the Hubble Space Telescope revealed something astonishing. In the planet's atmosphere, scientists found the clear spectral signature of water vapor. This discovery sent shockwaves through the field of astrobiology because it challenged a fundamental assumption. We had always searched for rocky planets with Earth-like atmospheres, but here was a different kind of world, one that might host a completely alien form of habitability. From this puzzle, a revolutionary new concept was born: the Hycean world. Hycean, a blend of the words hydrogen and ocean, describes a hypothetical class of planets with three key features. First, a massive hydrogen-rich atmosphere, many times thicker than Earth's. Second, beneath that crushing atmospheric envelope, a global, planet-wide liquid water ocean, potentially hundreds of kilometers deep. And third, a hot, high-pressure interior with a rocky or icy core. Think of it not as a solid planet with an ocean on top, but as a vast planet-wide sea capped by an immense sky of hydrogen. This model turns our search parameters upside down. On a traditional rocky world in the habitable zone, the surface pressure and temperature must be just right to keep water liquid. On a Hycean world, the ocean's state is governed from above. The thick hydrogen atmosphere creates an intense greenhouse effect, trapping heat from the star. But it also creates immense pressure at the ocean's surface. This combination of high pressure and high temperature could maintain liquid water even on a planet that receives far less stellar heat than Earth, or one that is tidally locked to its star. Suddenly, the habitable zone is not a narrow band, but a much wider swath of possibility. Planets previously dismissed as gaseous mini-Neptunes, especially those around calm red dwarf stars, could be prime candidates for this strange form of life. Their global oceans, sealed under that hydrogen blanket, would be protected from stellar radiation and cosmic rays. The water itself, under such extreme pressure, might not even boil until it reaches temperatures of several hundred degrees Celsius, creating a stable, if utterly alien, aquatic environment. The chemistry of life there would be profoundly different. Without a rocky surface interacting with the atmosphere, the cycles we rely on would not exist. Instead, life would have to thrive in a dark, high-pressure abyss, possibly drawing energy from chemical gradients at the ocean floor or from the faint starlight filtering through the immense atmosphere above. K2-18b is the first serious candidate for this new class of world. Subsequent observations with the James Webb Space Telescope not only confirmed the presence of water vapor, but also detected methane and carbon dioxide in its atmosphere, while finding scant evidence for ammonia. This chemical mix is exactly what scientists would predict if a hydrogen-rich atmosphere were in contact with a vast liquid water ocean. The search is no longer just for a second Earth. It is for an entire universe of possibilities we are only beginning to conceive, where life might not need a familiar shore, but could flourish in the eternal, pressurized dark beneath an alien sky. The chemistry of an alien sky is written in the colors of its star. For decades, that text was unreadable, a faint signal drowned in stellar glare. All that changed with the arrival of a new eye on the cosmos. The James Webb Space Telescope is not just another observatory. It is a revolutionary machine built to decode the atmospheres of distant worlds. Its primary tool for this task is a technique called transmission spectroscopy. Here is how it works in simple terms. When an exoplanet transits in front of its star, a tiny sliver of the star's light passes through the thin, glowing rim of the planet's atmosphere. The gases in that atmosphere act like a chemical filter, each one absorbing specific colors or wavelengths of that starlight. Webb's immense gold-coated mirror collects this incredibly faint filtered light. Its powerful spectrographs then break that light into an exquisite rainbow, a spectrum. Within that spectrum are dark lines, missing colors that form a unique barcode. Each line corresponds to a specific molecule. A dip at one particular wavelength might mean water vapor. A set of lines at another could signal methane. Another pattern might reveal carbon dioxide. This is how we read the air of a world we will never touch. The ultimate goal is to find biosignatures, chemical combinations that strongly suggest the presence of life. The classic example is oxygen and methane existing together in an atmosphere. On Earth, these gases react with each other and would quickly disappear unless they were constantly replenished, which life does through photosynthesis and biological processes. Finding them together on another world would be a powerful, though not definitive, hint. But Webb can look for more than just natural signs. It can also search for technosignatures, the chemical fingerprints of an advanced civilization. The most discussed are chlorofluorocarbons, or CFCs, synthetic compounds used in refrigeration and industry. These molecules have no known natural process that creates them in significant quantities. Detecting CFCs in an exoplanet's atmosphere would be a staggering discovery, evidence of technology, of industry, of another mind looking back at the universe. Yet this search is fraught with immense challenges. The signal is unbelievably faint, often 1 part in 10,000 or less of the star's total light. The observations require multiple, perfect transits, taking hours of precious telescope time for a single data point. And then there is the interpretation. A thick, Venus-like atmosphere of carbon dioxide could also produce signals that mimic some biosignatures. A water vapor detection might simply come from a lifeless, steamy world. The first atmospheric analyses of habitable zone planets from Webb have been a mix of revelation and mystery. For some promising worlds, like those in the TRAPPIST-1 system, early data suggests they may have thin or even no substantial atmospheres, perhaps stripped away by their red dwarf star's active youth. For others, like the mini-Neptune K2-18b, the data revealed that complex chemical soup of water, methane, and carbon dioxide, fueling the Hycean world hypothesis. Each observation, whether a detection or a non-detection, is a crucial piece of the puzzle. Webb is teaching us not just which worlds have air, but which ones can keep it and what that air is made of. It transforms the habitable zone from a theoretical space into a list of addresses where we are now reading the mail, searching for a letter that says we are here. The air of a living world tells a story in chemistry. We call these chemical clues biosignatures, the unique fingerprints left by biological activity in a planet's atmosphere or on its surface. They are not a single, simple molecule, but rather patterns and combinations that are difficult to explain through geology alone. The search for them is the heart of modern astrobiology, but it requires us to distinguish between mere habitability and the actual signature of life. First, we have the generic signs of a habitable environment. The presence of water vapor in an atmosphere suggests the potential for liquid water. Carbon dioxide indicates an active carbon cycle and a possible greenhouse blanket. Methane can be produced by volcanic activity or the interaction of water with rock. These are the building blocks, the stage upon which the drama of life could be performed. But they do not confirm that the play has begun. A potential biosignature is something more. It is a chemical configuration that, on Earth, is strongly linked to living processes. The classic example is the coexistence of molecular oxygen and methane. Oxygen is a highly reactive gas. It wants to combine with other elements, rusting metals or reacting with organic compounds. Methane provides the perfect fuel. In an atmosphere without life, these two gases would quickly cancel each other out. Their persistent presence together suggests a constant planet-wide replenishment. On Earth, that replenishment comes from biology, from photosynthesis pumping out oxygen, and from microbes and other life forms producing methane. Another powerful biosignature could be a gas wildly out of chemical equilibrium. A planet's atmosphere, left to purely geological and chemical processes, will eventually settle into a stable balance, finding a gas that should not be there in such high quantities like phosphine, which on Earth is produced by certain anaerobic bacteria and industrial processes, is a major red flag. We might also look for the spectral signature of surface pigments, like the red edge of chlorophyll that plants on Earth reflect. A world that shows a specific, unexplained tint in the light reflecting from its continents could be covered in an alien form of photosynthesis. Yet this search is a minefield of false positives. Context is everything. Oxygen, the gas we breathe, can also be produced abiotically without life through a process called photolysis, where ultraviolet light from a star breaks apart water molecules in the upper atmosphere. A planet with a thin atmosphere and lots of water vapor might build up a small oxygen signature this way. Similarly, methane can bubble up from geothermal vents in a completely sterile world. This is why astronomers do not seek a single magic bullet but a suite of evidence. The simultaneous detection of oxygen, methane, and water vapor, along with the absence of gases that would destroy that balance, forms a much stronger case. The planet's place in the habitable zone, its potential for liquid water, and its geological context all become part of the argument. A biosignature on a scorching hot world orbiting a blue giant star would be far less credible than the same signal from a temperate, rocky planet around a quiet sun. The ultimate interpretation will be a statistical one, a weighing of probabilities. Is the simplest explanation for this bizarre atmospheric cocktail a billion unseen microbes or a strange, previously unknown geological process? The first definitive discovery will likely be a whisper, not a shout, a pattern of spectral lines that makes the scientific community hold its breath and ask, what else could it possibly be? Biosignatures listen for the quiet hum of biology, but what about the roar of a civilization? Alongside the search for natural chemistry, a parallel quest scans the cosmos for technosignatures, the deliberate or incidental markers of advanced intelligence. These are not the fingerprints of microbes, but the signatures of engineers, of beings who have learned to manipulate their world and their star on a staggering scale. While biosignatures might be found on any habitable world, technosignatures require us to look at those same promising systems and ask a different question. Could someone there be looking back? The most famous technosignature search listens for structured radio signals. For over half a century, projects like SETI have scanned the sky, hoping to catch a narrow-band radio transmission, a deliberate beacon, or a leaked broadcast from another world. It is a search for a cosmic hello, a signal that carries the unmistakable pattern of design, unlike the random static of pulsars or interstellar gas. But radio is just one channel. Another possibility is pulsed laser communication. A powerful, focused laser beam flashing in a complex code could be an even more efficient way for an advanced species to signal across the interstellar dark, a lighthouse beam cutting through the noise. Other technosignatures would be visible not in communication but in colossal engineering. Imagine a civilization so advanced it captures the entire energy output of its star. The theoretical concept is a Dyson sphere, a vast swarm of orbiting solar collectors encircling a sun. We would not see the structure itself from light years away, but we would see its profound effect on the star's light. The star would appear oddly dim in visible light, but glow brightly in the infrared as the captured stellar energy is re-radiated as waste heat. Astronomers have already catalogued stars with unusual dimming patterns like Tabby's star that sparked speculation about alien megastructures, though natural explanations like swarms of comets are more likely. The search continues for any stellar anomaly that defies all natural models. Perhaps the most haunting technosignature would be one we are creating ourselves: atmospheric pollution. On Earth, we release industrial chemicals like chlorofluorocarbons or CFCs that have no natural source. These molecules are exceptionally durable and absorb infrared light in very specific ways. The James Webb Space Telescope, while searching for the biosignatures of oxygen and methane, could also theoretically detect the spectral signature of these artificial compounds in an exoplanet's air. Finding CFCS on a world in the habitable zone would be a profound and unsettling discovery. It would mean we are not looking at a pristine garden, but at a civilization that has reached and perhaps surpassed our own industrial stage. It would be evidence of another intelligence that has also learned to reshape its planet for better or worse. This dual search for both the natural and the engineered reframes the habitable zone. It is no longer just a cradle for life, but a potential stage for civilizations. Every star we find with a promising rocky planet now holds two layers of mystery. Does its atmosphere show the gentle chemistry of a living world, or does it bear the sharper marks of a technological one, or could it one day show both? The silence of the cosmos so far is not an answer, but an invitation to listen more carefully across every wavelength for the faintest echoes of another mind building fires in the dark. The galaxy seems to promise a crowded neighborhood of possibilities, from watery Hycean worlds to ancient super-Earths. Yet, when we point our most powerful instruments at the stars, we hear only a profound and puzzling silence. This contradiction has a name, the Fermi paradox, and it asks a deceptively simple question. If the universe is so vast and so old, and if life is statistically likely, then where is everybody? The discovery of thousands of habitable zone planets does not solve this paradox, it deepens it. We now know the real estate is there in staggering abundance. So the silence feels louder, more significant. Several compelling and sometimes unsettling ideas attempt to explain the Great Quiet. One of the most discussed is the concept of the Great Filter. This theory suggests that there exists an extremely difficult step, a cosmic bottleneck, that prevents life from advancing to the stage where it can colonize stars or make its presence widely known. The terrifying implication is that this filter might still lie ahead of us. Perhaps the transition from single-celled life to complex multicellular organisms is far more improbable than we think. Or maybe the leap to technological intelligence is the rare event. But if the filter is behind us, then the development of life itself was the miracle, and we might truly be alone. A more hopeful yet strange idea is the zoo hypothesis. It proposes that advanced civilizations are indeed out there, and they are aware of us, but they have chosen to observe without interference, placing Earth in a kind of cosmic wildlife preserve. They are letting our civilization develop naturally without contact to see what path we choose for ourselves. This presumes a level of universal coordination or ethical agreement that is difficult to fathom, but it would explain the lack of obvious visitation or signals. Another possibility is that technological civilizations are inherently self-limiting. They may be brilliant flashes in the cosmic dark, burning brightly for only a few centuries before succumbing to their own creations, whether through environmental collapse, nuclear war, or technologies they could not control. The window for broadcasting one's existence to the galaxy might be tragically short, or intelligence might not follow the path we assume. A civilization that masters virtual realities or inner contemplation might have no desire to explore the stars or send radio signals. Their entire existence could be inward-focused, leaving no trace for distant telescopes to find. The silence we perceive may not be an absence of life, but an absence of life that communicates in ways we can recognize or care to notice. Each new habitable world we find adds another data point to this grand puzzle. Are we looking at a gallery of empty stages, a universe of quiet observers, or a graveyard of possibilities that never quite made it? The search for an answer is not just about finding life, but about understanding our own place in a story whose ending we have yet to write. The profound silence of the cosmos presents a challenge, but what if we refuse to wait for a perfect world? If the galaxy does not provide a ready-made Earth, could we build one ourselves? This is the audacious dream of terraforming, the process of deliberately altering a planet's environment to make it habitable for Earth-like life. It moves us from passive observation to active creation, a futuristic lifestyle defined not by finding a home, but by building it from the ground up. The most likely candidate in our own solar system is Mars. It sits on the outer edge of the Sun's habitable zone and possesses the raw ingredients we would need: frozen water and abundant carbon dioxide locked in its soil and polar ice caps. The goal would be to push its climate over a threshold, triggering a runaway greenhouse effect in reverse to warm the planet and thicken its atmosphere. The first colossal step would be to raise the global temperature. One theoretical method involves constructing giant orbital mirrors kilometers across to reflect concentrated sunlight onto the Martian polar caps. The focused heat would vaporize the frozen carbon dioxide, releasing it into the atmosphere. Since carbon dioxide is a greenhouse gas, this would trap more solar heat, warming the planet further and vaporizing even more carbon dioxide from the soil, a positive feedback loop. Another idea proposes manufacturing super-potent greenhouse gases like perfluorocarbons in factories on the surface to jumpstart the warming process. As temperatures rise, the vast reservoirs of water ice locked underground and at the poles would begin to melt. This would create flowing water, the first rivers and shallow lakes on Mars in billions of years. With liquid water and a thicker, warmer carbon dioxide atmosphere, the planet would transition from a frozen desert to a cold but potentially livable world. The next phase would be biological. We would introduce engineered extremophile microbes, bacteria and algae designed to survive the harsh Martian conditions. Their mission would be twofold. First, to begin converting the carbon dioxide atmosphere into oxygen through photosynthesis. Second, to help create soil by breaking down the Martian regolith and releasing nutrients. This is a process that on Earth took microbes hundreds of millions of years, and we would be attempting to accelerate it on a planetary scale. The practical dimensions are almost beyond comprehension. The energy requirements alone would dwarf all human industry combined. The timescales involved are not measured in years, but in centuries or even millennia. It would be a project for generations, a commitment stretching further into the future than our recorded history reaches into the past, and this leads to the profound ethical questions. Do we have the right to fundamentally alter another world, to overwrite its natural history, even if it is currently a sterile desert? If microbial life exists in subsurface aquifers on Mars, our terraforming efforts would constitute an act of planetary genocide, wiping out the very native life we sought to find. Furthermore, who would this new world be? For the process of creating a breathable atmosphere could take tens of thousands of years. Who would govern this centuries-long project, and how would we ensure its benefits are shared equitably? Terraforming forces us to confront our role in the universe, not just as explorers but as architects. It asks if our destiny is to accept the worlds we find, or to reshape them in our image, carrying the blueprint of Earth with us to the stars. Building a new Earth is a monumental task, but reaching one is an odyssey that defies our current understanding of physics and human endurance. The nearest potentially habitable world, Proxima Centauri b, is a staggering 4.2 light-years away. That distance is not just a number, it is a chasm. With today's fastest chemical rockets, a journey there would take over 70,000 years. To cross such a void, our very concept of a spacecraft and of a human lifespan must be utterly reimagined. The first and most sobering concept is the generation ship. This is not a vessel for a crew, but a self-contained world for a civilization. It would be a colossal ark carrying thousands of people on a voyage lasting centuries. Multiple generations would be born, live, and die within its metallic walls, knowing only the artificial suns of its light wells and the recycled air of its biospheres. Their entire culture, history, and purpose would be the ship itself, with the distant goal of planetfall belonging to their far future descendants. The engineering challenges are beyond formidable. You must create a perfectly balanced, closed ecological system that can sustain human life without failure for hundreds of years, recycling every drop of water and molecule of oxygen. You must shield its inhabitants from cosmic radiation and the psychological toll of endless star-filled monotony, and you must maintain social stability, preventing societal collapse or the loss of the mission's core knowledge over generations. It is less a journey and more the deliberate launch of a floating city into an abyss, betting on the resilience of our distant grandchildren. A slightly less daunting alternative is the sleeper ship or cryogenic ark. Here, the crew is placed into a state of suspended animation, their metabolism slowed to near zero for the duration of the voyage. The ship, piloted by sophisticated artificial intelligence, becomes a silent tomb carrying frozen dreams across the light years. This solves the problem of generational drift and resource consumption, but introduces the profound biological mystery of whether human consciousness can be safely paused and revived after centuries. The technology to reversibly cryopreserve a complex human body, protecting its cells from ice crystal damage, remains firmly in the realm of science fiction. Both these concepts accept the grim tyranny of distance and time. They are voyages of profound sacrifice, but what if we could cheat? This is where breakthrough propulsion physics enters, ideas that seek to bend the rules of spacetime itself. One of the more plausible, yet still immense, concepts is nuclear pulse propulsion. Imagine a spacecraft that detonates atomic bombs behind a giant pusher plate, riding the shockwaves of successive explosions to build up a substantial fraction of light speed. Studied in projects like Orion, it is terrifyingly brute force, but theoretically within the realm of known physics. It could cut the journey to Alpha Centauri down to a century, a human lifetime, though it would require mining asteroids for thousands of nuclear devices. More elegant are light sails, enormous, ultra-thin mirrors pushed by the physical pressure of light itself. A powerful ground-based laser array could beam energy onto such a sail, accelerating a small robotic probe to perhaps 20% of light speed, reaching a nearby star in decades. This is the premise of initiatives like Breakthrough Starshot, which envisions sending gram-scale probes to Alpha Centauri within a generation. For human travel, however, the sail and the laser would need to be planet-sized. Then there is the ultimate dream, the warp drive. Based on the theoretical work of physicist Miguel Alcubierre, it proposes not moving through space, but contracting space-time in front of the ship and expanding it behind, creating a bubble that carries the vessel at effective speeds faster than light. The ship itself would be motionless inside this warp bubble, avoiding the relativistic effects of near-light-speed travel. The catch is astronomical. Current mathematics suggests it would require negative energy, a form of exotic matter that may not exist, and energy equivalent to the mass of Jupiter. It is a beautiful equation on a chalkboard, but for now, an impossible engine. These are not merely transportation plans, they are blueprints for the ultimate lifestyle change. Choosing to embark on such a journey, whether awake or asleep, is a commitment to a future utterly disconnected from Earth. It means accepting that everything you know, every forest, every ocean, every mountain on your homeworld will be gone, transformed by millennia of time before you even reach your destination. You are volunteering for a life and for your children's lives defined by a metal horizon for the sake of a shore you will never see. This transforms the habitable zone from a scientific category into a profound human question. Is a new world, glimpsed only in data and dreams, worth the cost of 1,000 lifetimes spent in the dark? Your home would have no sunrise and no sunset. On a tidally locked world like Proxima Centauri b, the sky is frozen in time. One hemisphere forever faces its dim red sun, a permanent, bloated orb hanging motionless in a burnt orange sky. The other side is plunged into an endless star-flecked night, so cold the very air might freeze and fall as snow. Life, if it exists, would be confined to the razor's edge between these two extremes, the Terminator line. This is not a line at all, but a vast twilight ring encircling the entire planet, a place of eternal dawn or dusk, depending on which way you walk. Here, the temperature gradients are not just seasonal, they are planetary in scale. The searing heat of the day side and the deep freeze of the night side would create a perpetual howling wind. Superstorms born from this ultimate temperature difference would rage eternally around the terminator, with winds screaming from the hot side to the cold, dragging moisture and weather in a never-ending torrential cycle. The weather patterns would be unlike anything on Earth, a global river of air chasing its own tail. In this strange ring of light, ecosystems would evolve in profound isolation. Plants, if they exist, would not track the sun across the sky. Their leaves might be black or deep purple to absorb every photon of the dim, red-shifted light, or they might grow in vast, flat sheets facing the unmoving star. Animal life would likely be nomadic, following the narrow bands of tolerable temperature as they subtly shift. The true action might be underground or deep in the oceans, where geothermal heat from the planet's core could create warm oases far from the chaotic surface. For humans, building a habitat here would be an exercise in extreme engineering. Settlements would likely be built underground or within heavily shielded structures to protect against the constant stellar flares from the red dwarf sun. The primary energy source would be starkly simple, solar power on the day side, but it would be relentless and constant. On the night side, the cold could be harnessed for industrial processes or cryogenic storage. The most stable place to live, ironically, might be directly within the storm belt of the terminator itself, in vast aerodynamic cities anchored to the bedrock, designed to channel the eternal winds for power. Life would be lived in a permanent, gentle twilight, with one half of the sky forever bright and the other forever dark. There would be no concept of a day, only a geography of light and shadow. Your entire world, your culture, your sense of time, would be shaped by your address along this single, life-giving ring. It is a reminder that a habitable zone planet is not a promise of a familiar home, but an offer of a completely new way to exist under a sun that never moves. The unmoving red sun is a stark reminder that life may cling to stranger shores. While we scan distant stars for Earth-like planets, some of the most promising habitats in our own solar system exist far outside any traditional habitable zone. They are not planets at all, but moons orbiting the giant worlds of Jupiter and Saturn. Here, in the frigid darkness, the warmth for life does not come from a star, but from a relentless gravitational embrace. Europa, a moon of Jupiter, is a world encased in a global shell of ice crisscrossed with cracks and ridges. For decades, scientists suspected what lay beneath. Then, data from the Galileo spacecraft confirmed it, a vast global saltwater ocean containing more liquid water than all of Earth's oceans combined. This ocean is kept from freezing solid by the immense tidal forces generated by Jupiter's gravity. As Europa orbits, the gravitational pull of the giant planet flexes the moon's interior, stretching and squeezing its rocky core. This friction generates enormous heat, a geological furnace that melts the ice from within, maintaining a dark, deep sea sealed under a frozen sky. The evidence is not just theoretical. The Hubble Space Telescope has observed plumes of water vapor erupting from Europa's south pole, geysers shooting material from the hidden ocean hundreds of kilometers into space. It is as if the moon itself is offering us a sample. The upcoming Europa Clipper mission will fly through these plumes, analyzing their chemistry for the building blocks of life. But Europa is not alone. Around Saturn, the small, icy moon Enceladus performs an even more dramatic display. From fractures at its south pole, enormous cryovolcanic plumes constantly erupt, jetting water ice, organic molecules, and salts into space. The Cassini spacecraft flew directly through these plumes and made a stunning discovery. The water is salty. It contains simple organic compounds like methane and carbon dioxide. And most importantly, it shows the chemical signature of hydrothermal activity on the seafloor. This means the subsurface ocean of Enceladus is not just a cold, dark pond. It is likely interacting with a hot, rocky core, where mineral-rich vent fluids mix with the water, creating the kind of energy-rich, chemically diverse environment that many scientists believe gave rise to life at the bottom of Earth's oceans. These discoveries shatter the old, sun-centric model of the habitable zone. They introduce the concept of the internal habitable zone, a pocket of warmth and liquid water generated not by starlight, but by planetary geology and gravity. A moon need not orbit in a star's Goldilocks band. It simply needs to orbit a massive planet in a way that keeps its interior churning. This realization expands the cosmic real estate for life exponentially. In our galaxy alone, there could be more subsurface ocean worlds than there are stars. Every gas giant system we discover around other stars may host its own family of icy, ocean-bearing moons, each a potential incubator in the cold dark. The search for life becomes a dual endeavor, looking outward to sun-warmed planets and inward to the hidden seas beneath the ice where life, if it exists, might flourish completely unaware of the concept of a sun, thriving in the eternal, gentle heat of a world's own restless heart. The hidden oceans of Europa and Enceladus are a testament to our ingenuity in finding life, but the next decade will see that ingenuity reach staggering new heights. A new fleet of observatories, both in space and on the ground, is being built with one explicit goal: to find and study a true Earth twin, a pale blue dot orbiting a sun-like star. The European Space Agency's Pluto mission, launching later this decade, is the dedicated hunter of such worlds. Unlike TESS, which scans the whole sky for bright nearby stars, Pluto will perform ultra-precise, long-duration stares at specific patches, focusing on stars similar to our own Sun. Its suite of 26 individual cameras will measure stellar brightness with unprecedented accuracy, allowing it to detect the faint, periodic dips caused by small, Earth-sized planets with long orbital periods. Pluto is not just looking for planets in the habitable zone, it is looking for planets with years like ours around suns like ours, building the catalogue of targets that are the most direct analogues to our own home. While Pluto finds them, the Nancy Grace Roman Space Telescope will attempt to see them. Roman carries a revolutionary technology called a coronagraph, an instrument designed to block the blinding light of a star with incredible precision. Think of it as an artificial eclipse generator inside the telescope. By suppressing that overwhelming glare, Roman's coronagraph will attempt to directly image giant exoplanets and potentially even large Neptune-sized worlds reflecting the light of their stars. This is a critical testbed for the technologies we will need to one day photograph something smaller and fainter, a rocky world in the habitable zone. The real game changer, however, will be here on the ground. The Extremely Large Telescope, or ELT, being built in Chile's Atacama Desert, will have a primary mirror 39 meters across, collecting more light than all of today's major research telescopes combined. With this colossal eye, astronomers will not just detect planets, they will analyze the chemical composition of their atmospheres in detail. By splitting the faint light of a planet directly imaged by the ELT, scientists could identify the biosignature gases we've discussed, like oxygen and methane, on worlds dozens of light-years away. It will turn atmospheric speculation into concrete chemistry, but to see an Earth, we must go even further. The ultimate dream is to block the starlight not inside the telescope but far away from it. This is the concept of the Starshade, a separate, flower-shaped spacecraft that would fly tens of thousands of kilometers in front of a space telescope, perfectly positioned to cast a deep shadow over the star while allowing the faint light of its planets to shine through. Working in tandem, a starshade and a powerful telescope could directly capture the image of a pale blue dot, a point of light whose color and spectrum would tell us if it has oceans, continents, and an atmosphere rich with signs of life. Beyond even that lies the potential of space interferometry, where multiple telescopes flying in precise formation act as one giant instrument, achieving a resolution so sharp it could map the cloud patterns on an exoplanet. These are not just missions, they are leaps of faith in engineering, each one designed to answer the single question that has driven us for generations. We are building the machines that will finally look upon another living world, not as a blurry date to point, but as a place, a story waiting to be read in the light of its alien sun. This relentless search for other Earths does something more than fill a catalogue. It quietly reshapes who we are. For centuries, humanity viewed itself as the center of creation, living on a unique stage set by the heavens. Then came the first great humbling, the Copernican revolution, which showed us Earth was not the center of the solar system. We were demoted from the central throne to a planet orbiting an ordinary star. The discovery of countless Goldilocks worlds is the second, and perhaps deeper, revolution. It extends the Copernican principle from astronomy to biology. If our position is not special, and our type of star is not special, and rocky planets in the habitable zone are not special, then why would the phenomenon of life itself be unique to us? This is the principle of mediocrity, not as an insult, but as a profound statistical likelihood. In a universe of such staggering scale and repetition, the extraordinary claim is that we are alone. The ordinary, even expected, reality is that we are one voice in a cosmic chorus. This shifts our self-perception from isolated accident to potential participant in a grand, universal story. But the true philosophical earthquake would come with a specific discovery, not just of a habitable world, but of a second genesis. Finding microbial life on Mars, if it arose completely independently from life on Earth, would be the most important scientific discovery in human history. It would mean that given the right conditions, the emergence of life is not a miraculous fluke, but a natural, almost inevitable chemical process. The universe would not just contain life, it would be biophilic, life-loving, predisposed to create it wherever the ingredients and conditions align. Imagine the implications. If life can spark twice in one single solar system, then across the galaxy, it must be as common as stars. Forests of alien trees might fill distant continents, and unseen creatures might swim in subsurface oceans on a million frozen moons. The silence we perceive would not be an emptiness but a distance, a simple matter of time and space separating conversations. This transforms the cosmos from a cold, silent vault into a potential living library, each world a volume in an epic story of adaptation and survival. It suggests that biology, not just physics and chemistry, is a fundamental part of the universe's expression. We would no longer be lonely explorers, but newcomers arriving late to a party that has been going on for billions of years, finally beginning to hear the faintest echoes of the music. The journey from a simple idea to a crowded galaxy has been breathtaking. We began by defining a narrow band of space around a star, a theoretical sweet spot where water could flow. We learned that this zone is not a fixed boundary, but a shifting ring of possibility shaped by the star's temperament and the planet's own resilience. We saw how Venus, inside this zone, became a scorched monument to a lost balance, and how Mars, on its fringe, faded into a frozen whisper of ancient rivers. Then, with telescopes like Kepler, we discovered this was not just theory. The cosmos is teeming with worlds. Thousands of candidates, then confirmed planets, emerged from the data, revealing that small, rocky planets are the most common type in the Milky Way. TESS brought the search closer to home, finding prime targets around bright, nearby stars. And now, with the James Webb Space Telescope, we are no longer just counting worlds. We are reading the chemistry of their skies, searching for the subtle fingerprints of water, methane, and perhaps one day, the unmistakable signs of a living biosphere. We stand at a remarkable threshold, a golden age of cosmic discovery. For the first time in human history, we possess the tools not just to wonder about other Earths, but to find them, study them, and listen for their stories. We are on the cusp of potentially answering one of humanity's oldest and most profound questions. Are we alone in the universe? Every new atmospheric spectrum, every flicker of a distant star brings us closer to that revelation. This is not just science, it is a shared human adventure. So stay curious, follow the data as it streams in from missions like James Webb and the upcoming Roman and Plato telescopes. Read the headlines about strange new atmospheres and ocean worlds, and the next time you look up at the night sky, remember this: every point of light is not just a star. It is a sun, likely surrounded by its own family of worlds. Some of those worlds are rocky, some are warm, some may have liquid oceans and skies filled with complex chemistry. And on one, perhaps someone might be looking back at our pale dot of light, wondering the very same thing. The universe is speaking, we have only just learned how to listen.